Okay, like I said before, we're going to continue on here and talk about some now really the main part of the chapter here, which is colligative properties. And colligative property solutions basically depend on the number of particles that are dissolved in it. And basically, the idea here is if you had something, say, like water by itself, just a solvent, and you have these solvent molecules in, say, obviously the solution. If you wanted to take it to, say, its boiling point, there's really kind of nothing in the way. It's going to be able to have sort of a free passage, if you will, to sort of escape the solution at its normal boiling point. Also, if they wanted to sort of come together to freeze or something like that, they also would be able to kind of do that without anything really getting in the way. Now, the idea of colligative properties is you have this solvent in there, but you decided to dissolve some solute in it, some other particles. So now you have some other particles sort of dissolved in there with your solvent. And now what happens is because you have these other particles sort of dissolved in there, it's a little bit more challenging for these guys to try to get around and kind of escape sort of the solution if they wanted to boil, they got to kind of go around all these things. Also, if they wanted to come together, there's now all these other guys in the way, basically, and that's going to kind of get in the way. So these properties here are colligative properties are based on these particles that are present. The more particles that are present, really the more it sort of gets in the way. And what it affects in a lot of cases are things like freezing points of a substance. It will affect things like the boiling point of a substance. It will also affect things like the vapor pressure of a substance. And again, it's all due to these extra sort of particles that are in the way, and it causes things to occur at, say, different temperatures. For example, in terms of freezing point, it will typically lower the freezing point. So you have to remove a lot more energy because there's a lot more stuff floating around in there. In terms of boiling point, as we'll talk about, it will actually increase the boiling point. So it takes a lot more energy for those guys to escape through that maze of all the particles that are in there. And for something like vapor pressure, it will actually lower it for really the same reason. It's going to take a lot more energy for those guys to escape. There's going to be a lot less guys able to escape the solution. So the first sort of colligative property of a solution is what's known as vapor pressure lowering. And as we talked about, vapor pressure is the pressure of the gas that's above the liquid. So at the surface of any liquid, as we talked about, there's molecules that are able to escape into the gas phase, and that's known as a vapor pressure or vapor. And because they escape, they apply a pressure above the liquid. And we can calculate this using Raoult's law here, and that is Pz, which is the vapor pressure of the component in the solution, is equal to the mole fraction of that component times the vapor pressure of the pure substance. So this is kind of like the pure substance. And this is really the solution that has stuff dissolved in it, obviously, to make a solution. And obviously, that is our mole fraction there. The vapor pressure lowering is defined as the vapor pressure of a pure substance minus the vapor pressure in the solution. So the idea here is in order to have vapor pressure, you got to get some vapor molecules above the liquid. Now, when you have, again, some solute dissolved in here, there's a lot of stuff in the way, for example. And that's going to cause actually less of those guys able to escape solution. And you'll have actually less vapor molecules over the solution. And that's going to mean less gas molecules over the solution. You're going to actually have a lower vapor pressure in this particular case. So let's take a look at sort of a calculation involving this. The vapor pressure of ethyl alcohol at 66 is 66.5 torr. We want to calculate the vapor pressure of ethyl alcohol in a solution if 0.2 moles of glucose is dissolved in 1.25 moles of the alcohol. So we have a couple of things here given to us. We have our vapor pressure here of ethyl alcohol. So our normal vapor pressure is 66.5 torr. We want to use our vapor pressure lowering is our mole fraction times our initial here. So we do want to calculate the mole fraction here of our ethyl alcohol. And that's going to be the moles of our ethyl alcohol, which is 1.25 moles, divided by our total moles, as we just talked about. So that's going to be our 1.25 plus our 0.2 moles. And that'll give us our total moles. And that's going to give me here 1.25 divided by 1.25 plus 0.2. It's going to give us a mole fraction of 0.8621. So now we have this guy and we have the vapor pressure of this ethyl alcohol by itself. So our vapor pressure lowering in this case will be our 0.8621 times the vapor pressure of our ethyl alcohol that's kind of pure there, which is our 66.5. And that will get us here a vapor pressure of 57.3 torr. So with nothing dissolved in ethyl alcohol, we're getting a pressure of 66.5 torr. With this glucose, which is basically the solute particles that are dissolved in there. Glucose is non-ionic, right? It's carbon, hydrogen, and oxygen. It's covalently bonded, so just one molecule per. It actually lowers the vapor pressure down to 57.3. So essentially the glucose molecules are getting in the way of the ethyl alcohol being able to escape solution and go into the gas phase. And because of that, we have less gas molecules above the liquid. The result of that is a less pressure above the liquid, and the vapor pressure actually comes down. Any questions on that calculation there? And there it is, much neater than my finger. Maybe you wrote it. There we go, in case you need to see it. Now, another colligative property that's affected by the presence of sort of particles in solution is freezing point. And the way it affects it is what's referred to as freezing point depression. And it basically will actually lower the freezing point. So where a solvent by itself with nothing dissolved in it would freeze. So for example, water is 0 degrees Celsius. If you dissolve some salt in it, like sodium chloride or rock salt or whatever you want to put in there, the presence of those particles, again, you could think of it as going to get in the way of the natural process of like the water molecules coming together to freeze. And it's going to take a lot more energy being removed for that to occur. And you're actually going to lower the freezing point of that solution where you have the solid dissolved in it. So we do have an equation for that, and that is delta T. Whoops, come back. That is, if I hit it there, delta T F, and that is the change in freezing point temperature. So that is the change in freezing point temperature is equal to Kf times M. M is our molality, so that is our moles over kilograms of solvent that we talked about. Kf is a constant. This is the freezing point constant. Now, this is a value that you could find on the table, and it's really important that you understand that this value is based off of the solvent. So if you go to a freezing point table, you will not find the solution you're dealing with. You will find basically just the solvent listed, which is, for example, water. So don't be surprised if you go there, you can't find like sodium chloride or anything like that. It will just be basically a table of solvents, and that is what you should look at. Now, because the freezing point in this case is lower than it is in the solvent by itself, to find the change in freezing point temperature, we take the temperature of the solvent, which is actually going to be a higher number, minus the temperature of the solution that has stuff dissolved in it, and that will give you the correct way. So you definitely want to do solvent minus solution here. If you do it in the opposite direction, you will add when you should subtract, or subtract when you should add. So you want to make sure that you do solvent minus solution here. This is the equation for change in freezing point temperature. And this is when we add something that is non-ionic to a solution. So again, basically sort of molecular compounds or non-ionic compounds to a solution. Now, boiling point is elevated in this situation. So for example, water by itself will boil at 100 degrees Celsius. If you dissolve some non-volatile, which basically means non-ionic, solute particles in water, you will actually increase the boiling point, basically, of water, and it will not boil at 100 degrees, but it will boil higher than 100 degrees. And again, it is those particles that are dissolved in that solution that gets in the way of it dissolving. There is a similar formula for boiling point, and that is the change in the boiling point temperature. And that is what that is. That's the change in boiling point temperature is equal to Kb times our molality. So again, that is our molality, which is our moles per kilogram. This is the boiling point constant. And that also is based off of the solvent. So again, when you go to that table, it is the solvent that you want to go and look up for. Now, in this particular case, because the solution will actually boil higher than the solvent by itself, when we do the change in boiling point temperature, it is opposite of freezing point. You actually want to take the solution's temperature minus the temperature of the pure solvent. And again, that will give you sort of adding and subtracting correctly in this particular case. Boiling point elevation, freezing point depression. That, for example, is what antifreeze does in your car. It does both. It lowers the freezing point. So if you live in a really cold environment, the water in your car doesn't freeze. And it also will raise the boiling point. So if you live like in Arizona, a really hot environment, it will not overboil and overheat your car. And that's basically what antifreeze does for your car. Any questions on that there? Though this is also the formula for non-ionic, non-volatile solutes that are dissolved in it. So let's take a look at one here and see, actually, let's take a look at the actual table here. So this is a table similar to one you have in your book of solvents. So what we got going on here are solvents. And on the left, and we have the normal freezing point temperatures, and we have our Kf value and Kb value. It is important to remember that if water is not the solvent, so if it is not water, but maybe it's something, one of these guys, they will have different freezing points and different boiling points. So you don't want to use 0 and 100 for something that's perhaps not water because it might not be the correct temperature. I would say water is oftentimes used a lot, but it's not always a solvent. That is our freezing point constant 1.86. And that is our boiling point 0.512 for water, where water freezes at 0 degrees and boils at 100 degrees Celsius in this particular case. All right, so let's take a look at how we would work one of these. What is the freezing point of a 1.7 molal solution of ethylene glycol? And in this case, a couple of things here that we want to kind of note, which is Aqueous, which means water is most likely going to be your solvent in this case. That is why when we go to the table here, we're going to be looking for the Kf value for water, which is 1.86. Since we're dealing with freezing point, the freezing point is based off of the solvent as well. So the normal freezing point for water is 0 degrees Celsius in this case. In this particular case, we could use our change in freezing point temperature is equal to our Kf times our molality. In this particular case, they were nice enough to give us the molality. If they don't, then you need to calculate it. So it's very common you'll need to calculate it as well. So we have our molality. We also have our freezing point constant. So we can put this into our equation. The change in freezing point temperature is equal to our Kf for water, 1.86 degrees Celsius divided by the molality, times the molality of 1.7. The molality will cancel. That's going to leave us degrees Celsius, which is good because that is a temperature, which is what we're looking for. And that will get us something like, we'll call it 3.16 degrees Celsius. Now, it's really important when you do these problems that you read carefully. We are looking for the freezing point temperature of this guy. This number here is not the freezing point temperature. This is the change in freezing point temperature. So this is where we're talking about kind of solvent minus solution or solution minus solvent temperature comes into play. Because this is freezing point depression, that means that the solution will actually freeze at a lower temperature. So our change in freezing point temperature will be our temperature of the solvent where it freezes minus the temperature of the solution. That means if I want the temperature of the solution, it will equal the temperature of the solvent minus the change in freezing point temperature. So in this case, water normally freezes at 0 degrees Celsius minus our change in freezing point temperature that we just calculated, which is 3.16 degrees Celsius. This will give us a temperature for the solution of negative 3.16 degrees Celsius. And that is the answer we're looking for. Remember, it is freezing point depression, which means by putting in this ethylene glycol into water, instead of our water freezing at 0 degrees, it's actually going to freeze lower. It's going to freeze at negative 3.1 degrees Celsius. Any questions on that? If you gave the answer at 3.16, your freezing point is going in the wrong direction. It actually froze at a higher temperature. So again, that's why it's really important to understand for freezing point this relationship so that you add or subtract correctly depending on the question. Any questions on that there? Okay, so why don't you, that's the one we just did. So I'll scribble that out there so you can see it. All right, so why don't you try this one? Why don't you see what you come up with on this? Give it a go. We want to calculate the molar mass. So molar mass is grams per mole, right? So see how you could get all that. Of a compound, if a solution of 12 grams is dissolved in 80 grams of water and it freezes at minus 1.94 degrees Celsius. All right, so let's take a look and see. In this case, we're looking for grams per mole, which is the molar mass. And in this case, we want to see if we have any of that information. So we're looking for the mass of a compound if a solution of 12 grams of it's dissolved. So I'm going to say right off the bat, I have my grams part right there, which is the 12 grams. In 80 grams of water, so this is our solvent. Go down our solvent there. As that is our water here, and it freezes at negative 1.94. So we know obviously water's our solvent, so we can look up in our table our Kf value for water. We also again know that the normal freezing point of water is 0 degrees Celsius. So we can use our formula here to help us. Our freezing point, change in freezing point temperature is our Kf times our molality. So I definitely have that. I could figure out my change in freezing point temperature. That would allow me to figure out my molality. And my molality is moles of solute divided by kilograms of solvent. And that would allow me to get the molality, and I know how much solvent I have, which means I could get rid of my solvent and figure out the moles, basically. So I can use the freezing point information to figure out the molality of the solution. And because I know how much solvent I have, I could then use that to get the moles, which is the missing part. So it is important to also, again, remember that what they gave you is the temperature at which this solution freezes, and that's negative 1.94 degrees Celsius. That again is not the change in the freezing point temperature. So the change in the freezing point temperature is the temperature of our solvent minus the temperature of our solution. The temperature of our solution in this case will equal the temperature of our solvent minus the change in the freezing point temperature. So that's going to be 0 degrees minus a minus 1.94 degrees Celsius. That is how the negative goes away, basically, here. So minus minus gives us that this temperature, our change in freezing point temperature, is going to be 1.94 degrees Celsius. So that will give us our change in freezing point temperature will equal basically this here. So now that we have the actual change in freezing point temperature, we could put it in there, and that would get us that our molality in this case would be our change in freezing point temperature divided by our Kf. That would be 1.94, again, should be positive, divided by our Kf, which is for water, which is our solvent, degrees Celsius over molality. So if I do that there, we will end up with 1.94 divided by 1.86. That is going to get us here a molality of 1.04 little m in that case. Any questions on that so far? Now that we have the molality, that's going to allow us to figure out the moles, which is what we're missing. So I'm going to kind of erase some stuff here. So I got somewhere to write, I think. Get rid of that too while we're at it. So we know in terms of our solvent, we have 80 grams. And we do need it in kilograms because that is what molality means. So there are 1,000 grams in a kilogram. And that's going to give us 0.08 kilograms, in this case, of solvent. So if we take our 0.08 kilograms of solvent and we multiply it by the molality we just calculated, which is 1.04 moles per kilogram of solvent, the kilograms will cancel each other out. Again, that is what the little m stands for, moles per kilogram. So if we take that times 0.08, gonna get us 0.0834 moles. That again is the bottom part of what we need. We have the top part, which was given to us. So now our molar mass here is going to be our 12 grams that was given to us in the problem, divided by our 0.0834 0.34 moles. So we'll take our 12 divided by that, and that's going to give us 143.8 grams per mole as our molar mass. So here we could use our freezing point information to figure out our molality, which will allow us to get to our moles and allow us to figure out something like our molar mass. Again, you want to be careful with numbers and negative signs and stuff like that, so that you end up in the right direction. Any questions on that particular one there? All right. That's the one we just did, I think. All right, so why don't you try this one then? We got how many grams of ethylene glycol must be added to a kilogram of water to give a solution that boils at 105 degrees Celsius? So just so you know, our boiling point here in this case, we want to go back to our table. And for our boiling point, it is our 0.512 for our water and 100 degrees Celsius. 0.512. Okay, so let's take a look at this one. Here we're doing boiling point. So again, we do need, obviously, as we just looked up there, the boiling point constant. Here again, we have water involved, which is going to be our solvent. And again, that is why we looked it up. We are also doing boiling point in this case, unlike the freezing point in the last couple of examples. So boiling point for water is normally 100 degrees Celsius. So again, you want to make sure you're using the correct temperature here in this case to help you out. Here again, we're looking for how many grams of our ethylene glycol, which is our solute that's dissolved in this solution. And really, we have just the freezing point sort of temperature. So once again, we could use our boiling point equation, which is very similar to the freezing point one. And we have the KB. We could figure out our change in boiling point. This once again will allow us to get to the molality, which is our moles of our solute over kilograms of solvent. And then we can figure out the moles of our solute, and then the molar mass will give us the grams of it. So once again, here we're going to use our boiling point information to kind of get to the molality and use that to figure out really what the question is asking for. Here the solution boils at 105 degrees Celsius. Remember, again, we need the change in boiling point temperature. And because the solution boils at a higher temperature, it is different than freezing point. It is the temperature of the solution minus the temperature of the solvent. That means in this case, the temperature of the solution minus the temperature of the solvent will give us that change in freezing point temperature. So putting that in is going to be 105 degrees Celsius minus the normal boiling point of water, which is 100. That gives us a 5 degrees Celsius as our change in boiling point temperature. So it is not 105 that you want to use in this calculation. You want the actual change from the solvent to the solution, and that's only 5 degrees in this case. Any questions on that there? Now that we have that, we can solve for molality, and that would be the change in the boiling point temperature divided by KB. That again is the 5 degrees Celsius we just calculated, divided by our 0.512 degrees Celsius molality. The degrees Celsius is going to cancel out. It's going to leave us with molality. So 5 divided by 0.512, going to give us a 9.766 moles per kilogram, basically. That is what, again, molality stands for. That is good because the kilograms on the bottom is kilograms of solvent. And in this particular problem, they actually gave us the kilograms of our solvent, which is 1 kilogram. If they didn't, obviously, we would need to do a conversion. So we could actually just times this by our 1 kilograms of water. The good news is it's not going to change any number, but it will give us basically 9.766 moles of our C2H, what we got there? 6, I think, yeah, O2. 6O2. Now we can use the molar mass from the periodic table to calculate how many grams that would be. So that is 2 times 12.01 plus 6 times 1.008 for the hydrogen plus 32 for the oxygen. That is going to give us a molar mass from the periodic table of 62.07 grams per mole. The moles will cancel, and that will tell us that in this case, we would need about, we'll call it 606 grams of this ethylene glycol needs to be added to cause this water basically to boil at 105 degrees Celsius. Once again, here using molality to get to moles and obviously to our grams. Any questions on that one there? All right, try one more here. Boiling point. This is the one we just did, so I'll scroll this across in case you want to look at it better. My finger writing here on the tablet. There you go. Got that. About 610 they went with on significant figures. All right, so give this one a go. Calculate the actual boiling point of a solution that you make by dissolving 1 gram of glycerin in 54 grams of water. And again, since we are doing boiling point and we're doing water, we're using the same KB here for water, and that was 0.512, I believe. And obviously 100 degrees Celsius, our normal boiling point. All right, give it a go, see what you come up with here. Okay, so obviously here we're calculating the boiling point of solution made by dissolving 1 gram of glycerin in 54 grams of water. Once again, that is our solvent here, water, which is why we looked up, obviously, in the table, the correct values here for boiling point for water. We could use our equation here, the change in boiling point temperature, going to be our KB times our molality. In this particular case, we actually need to calculate the molality. We already have the KB, and that will allow us to figure out the change in boiling point temperature. So to do that, we will take our 1 gram of glycerin here, which is C3H8O3. C3H8O3. We'll go to the periodic table and calculate a little molar mass of that guy. So 3 times 12.01 plus 8 times 1.008 for the hydrogen, plus a 3 times 16 there for the oxygen gives us 92, looks like 09 grams per mole here. And that's going to give us 1 divided by 92.09. And that'll get us 0.01086 moles. We want to calculate the molality. So that is moles, which is what we just got there, 0.01086. divided by kilograms of solvent, which is 0.054 kilograms. That comes from our 54 grams of water converted into kilograms. So divide by 1,000 basically to get that there. And that gets us obviously our number on the bottom there. That's going to give us our molality here of 0.054. Looks like 0.2, we'll call it 0.01 molality there. Any questions on that there? Now we have basically everything that we need to calculate the change in the boiling point temperature. That's going to be our KB, which is 0.512 degrees Celsius molality, times our molality we just calculated, 0.201 little m. That's going to give us times 0.512, a 0.10 degrees Celsius. Once again, you got to remember that we're looking for the boiling point temperature. What we just calculated is the change in boiling point temperature. It is not the actual boiling point temperature of the solution. So this is where that relationship of the change in the boiling point temperature will be the temperature of the solution minus the temperature of the solvent where it normally boils. That would give us that the temperature of the solution here would be the change in boiling point temperature plus the temperature of the solvent. And that would be normal change we just got, which was 0.1 degrees Celsius plus our normal boiling point of 100 degrees Celsius gives us a whopping increase here in boiling point from 100 to 100.1 degrees Celsius in this particular case. It did go up a little bit, obviously. In this case, it went up 0.1 degrees Celsius. So it is really important in these, as I mentioned before, especially if you're asked freezing point temperature, boiling point temperature, that you actually do give that temperature and you don't just give the change in either freezing point or boiling point. You will probably be off in both cases. Boiling point, for example, with water, you'll be off by like 100. And if you just give the change in freezing point temperature for water, you'll probably be off by like a negative sign, or it should be negative or something like that. Any questions on freezing point depression, boiling point depression, things that you could calculate from it? Okay. The next sort of property of solutions we're going to talk about, and this is the one we just did, so let me scroll it across the screen there. Is osmotic pressure. And osmotic pressure is when a solution is separated from a solvent by a semi-permeable membrane. What happens is the process of osmosis. So if you have like a tube here, and you have a semi-permeable membrane, which is basically a membrane that allows certain size particles to flow through, restricts other size particles from getting through. Frankly, there's some particles that are too big for the holes to fit through, basically, and they get stuck and they can't get through it. So if you had, say, on one side of this membrane, just pure water, a little H2O, and let's say on the other side of the membrane here, you had salt water. The process of osmosis is this. Osmosis will basically make solvent molecules flow from a lower concentration to a higher concentration. That is the process of osmosis. So, for example, water molecules will flow from a lower concentration to a higher concentration. In the case of this example here, water by itself is a low concentration. It has nothing dissolved in it. By the way, pure water has no osmotic pressure because it has nothing dissolved in it, basically. Salt water is water with sodium chloride, for example, dissolved in it. So it has a lot of particles dissolved in it. It has a higher concentration. So the process of osmosis in this case will allow the water molecules to basically cross over to the saltwater side in an effort to basically dilute down the salt water and make it less concentrated in an effort basically to do that. It will continue to flow until it hits a pressure that is equal to basically the atmospheric pressure pushing back down on it. And that is what's known as the osmotic pressure. At that point, no more water molecules will basically flow to the other side. That's also the idea of reverse osmosis is you have a situation like this and you apply a pressure greater than osmotic pressure, and that will push everybody back the other way. And if you have a bunch of filters in there, you can catch all the stuff you don't want, and you get some pure water coming out the other direction, basically. And those filters and stuff will catch all that stuff. So we could calculate the osmotic pressure by using this equation here, which is this guy. That is the osmotic pressure. And it's a fancy symbol, but let's be honest, we've seen this equation before. This is our friend PV equals nRT, basically. This is the ideal gas law. It's the same gas formula that you use for osmotic pressure. They just use a few different symbols like the osmotic pressure symbol there, but that's basically just P. And that means that when you use this equation, which is really the ideal gas law, you need to make sure everybody's in the right units like it should be. Pressure, again, should be atmospheres. Volume should be liters. Temperature should be Kelvin. R is the same 0.08206 gas constant, and N should be moles. We talked about this when we were in the gas chapter, that if you solve for N over V, that is moles per liter, that is the molarity, right? Which is what that symbol is. So that is the molarity of the gas. So the nice thing is to calculate the osmotic pressure, it essentially is just the ideal gas law. And you could do things like we've done before, which is calculate things like molar mass using the ideal gas law. It's the same sort of calculation. So let's take a look at one of those. So we want to calculate the molar mass of a protein. If 5.87 milligrams per 10 milliliters gives an osmotic pressure 2.45 torr at 25 degrees Celsius. So first off, when we look at this, we're looking for our grams per mole here. So frankly, we have our grams. We just need to do a conversion, but we basically can convert our grams, our milligrams into grams, and we'll have it. Now, if we look at everything that's left over at this point, we have a volume that is 10 milliliters. We have a pressure that is 2.45 torr. And we have a temperature that is 25 degrees Celsius. So obviously it's talking about osmotic pressure. So that really is the ideal gas law, and I'm not going to hide it. I'm just going to use the ideal gas law here because why not? We have pressure, we have volume, we have temperature, we always have R. The one thing that we don't have is moles. And that's good because, frankly, that is the other thing that we need. So we're just going to use really the ideal gas law here to calculate the moles. We do have to do some conversions, obviously. So we need to convert our volume into liters. So our 10 milliliters, we're going to do 1,000 milliliters divided by a liter, going to give us 0.01 liters. We also need to convert our pressure into atmospheres. So 2.45 torr. We're going to use our 760 torr is an atmosphere. And that will get us 2.45 divided by 760. And that's going to give us 0.00322 atmospheres. And lastly, like all gases, we need to add a 273, and that will give us 298 Kelvin here for our temperature. So if we solve for N in this case, N will equal PV divided by RT. Putting in our values here are 0.00322 atmospheres, our volume 0.01 liters divided by our R, 0.08206 liters atmosphere Kelvin mole, and our temperature of 298 Kelvin. So that will give us our moles. So 0.00, that. We'll take that there times 0.01 divided by 0.08206 and divided by 298. Going to give us, in terms of moles here, not that. There we go. Going to give us 1.318 times 10 to the minus 6 moles. That is the bottom part for our molar mass. As I mentioned before, we do have to convert our milligrams that was given to us into grams. So we'll take our 5.87 milligrams and convert it into grams. 1,000 milligrams is a gram. So we'll take our 5.87 divided by 1,000. Going to give us 5.87 times 10 to the minus 3 grams that I can now divide by my moles of 1.318 times 10 to the minus 6 moles. And that should give me my molar mass for this particular guy, which looks like is going to be a fairly big number there. About, we'll call it 4454 grams per mole. Any questions on that particular one there? This is honestly the same calculation we did in the gas chapter about finding molar mass and density and that type of stuff, basically using the ideal gas law. Any questions on that one? All right, so why don't you try one then here? Why don't you try this one? What is the molar mass of a lysozyme if 0.075 grams per 100 milliliters gives an osmotic pressure of 1.32 times 10 to the minus 3 atmospheres at 25 degrees Celsius? Let's see what you come up with. Okay, so let's take a look. Once again, we're looking for our molar mass, which is grams per mole. So we're just going to see if we got anything there. And we do in this case. We do actually have the grams good to go right out of the bat. The rest here are going to be kind of our pressure information. So we got a volume that is 100 milliliters. We got a pressure there, 1.32 to the minus 3. 1.32 times 10 to the minus 3 atmospheres. And we have a temperature that is 25 degrees Celsius. So once again, since it's osmotic pressure, we could use our ideal gas law. We have temperature, we have volume, we have pressure, we always have R. So again, here we could use the ideal gas law to get the moles part of it. And we just need to do a few conversions here. So our volume, we're going to divide by 1,000. And that should get us to 0.1 liters. Our pressure is good in atmospheres. We will convert this to Kelvin. So we'll add 273 to it to give us 298. And once again, here we're going to solve for N, will be PV over RT. Pressure here are 1.32 times 10 to the minus 3 atmospheres. Our volume, that needs to be in liters because really this is the ideal gas law. Our R here. And our temperature, 298 Kelvin. Going to get us 1.32 to the minus 3 times 0.1 divided by 0.08206 divided by 298. Gonna get us here scientific notation because that's too many zeros at this hour. 5.398 times 10 to the minus 6 moles. Now that we have our grams and our moles, we could get our molar mass, which would be our grams, which was 0.075 grams, divided by our moles, 5.398 times 10 to the minus 6 moles. Going to get us here 0.075 divided by our answer. And we're going to get something like 1.39 times 10 to the 4 grams per mole. And it is a big protein, so it has a big molar mass. Yeah. Any questions on that there? So again, osmotic pressure calculation, pretty much identical to what we did in the gas chapter when we were talking about molar mass calculations, or just in general, just the ideal gas law calculation. If you were calculating just the osmotic pressure, it basically would just be P out of the ideal gas law. Any questions on that? Okay, so one last thing to talk about in terms of what we've been talking about to tie everything together. Up until this point, when we talk about the solute that we have been dissolving in a solution, it's been non-volatile or non-ionic. And what that means is, like, if you take something like ethylene glycol, any type of covalently bonded solute, when you go and take one molecule of that guy and put it into the solution, you basically get one molecule that goes in. Now, that is different than if you were to take a ionic compound like sodium chloride and toss it into water. When you would toss it into water, you would actually get a sodium ion and a chloride ion. You would actually get 2 particles for every one that went for a swim. And that's important because all these colligative properties are based off of how many particles there are in solution. So because when you get to something that's ionic, it will completely break apart, for example, in the solvent like water, you have to take that into account. And that's what's known as the von Hoft factor, which is I. And in this case for sodium chloride, I would equal 2. Basically, you have a sodium ion and a chloride ion. That's 2 particles floating around in it. If you had calcium chloride and put that into a solution of water, you would get a calcium ion and 1 and 2 chloride ions floating around. The I for this guy would be 3. Now, when you do something that's non-volatile or non-ionic, you only get a 1-to-1 sort of molecule. The I factor there is actually 1, which is why in all those equations that we used earlier, we didn't need to take it into account because it was basically a 1. You're basically multiplying by 1. You could add the von Hoft factor into those equations that we just saw, like our freezing point depression, our boiling point depression. So the change in the freezing point depression would be I times Kf times M. The change in boiling point would be I times Kb times M. Could also do it for vapor pressure lowering and incorporate it into that if you're doing something that's ionic as well. So you can incorporate that I into the vapor pressure lowering as well. It's really the exact same calculation, except that you do need to take into account the number of particles that are present in an ionic versus a non-ionic situation. Once again, the reason we didn't put these guys in earlier was everything we dissolved was non-ionic. So basically I was 1. So we just multiplied by 1 basically in this case. How does that make a difference? Let's just say that we had a sodium chloride solution that had a 2 molality, and we had a calcium chloride solution that was also 2 molal. And if we did something like our freezing point change in temperature, for sodium chloride, I would equal 2, as we just talked about, because you get a sodium and chloride. This would be 2 times our Kf of 1.86 degrees Celsius times molality, because water's our solvent, times 2. This would get us here 2 times 1.86 times 2 would give us a change in freezing point temperature of 7.44 degrees Celsius. That means instead of at 0 degrees Celsius, that solution will freeze at minus 7.44. Now, if you take the same mole solution, that is calcium chloride, I would equal 3 in this case because you get 1 calcium, 2 chlorides, more particles in that solution. Basically, we would put R3 or 1.86 degrees Celsius times molality times R2 molal. And that would give us 3 times 1.86 times 2. It will actually drop 11.16 degrees Celsius. Which one has a greater effect on the freezing point? It is the calcium chloride. And that is because it has more particles in that solution, more stuff to get in the way, going to take a lower freezing point to get it to freeze. Same thing would happen if we did the boiling point. We would see a greater elevation of the boiling point in the calcium chloride because there is more particles in that solution. So if you're dealing with anything that's ionic and these colligative properties, you do have to take the I into account, which is the von Hoft factor. And basically the rest of the calculation is the same. You just got to kind of take that into account. And you can basically do it and figure out I based off of the formula. Although in reality, if you do some experiments, it's not exactly perfect. But for any type of book problem that you're going to do, you basically could just use the I based on the formula. So here with K2SO4, you get 2 potassiums and 1 sulfate. That means that the I in this case would be 3. For FeCl3, you get 1 iron 3 floating around, and you get 3 of these chlorides floating around. I would equal 4. So again, that's the way you could calculate I and incorporate it into your calculation again when you're dealing with anything that is ionic, anything that is not ionic, non-volatile, non-ionic. I basically equals 1. So you could pretty much just do it like we were doing previously. All right, so let's take a look at this one here. What is the measured von Hoft factor if a 0.05 molal calcium chloride has a freezing point of minus 0.27? So here we're doing freezing point, and it is ionic, which is calcium chloride, so we do need to incorporate the I and our Kf and our M. In this particular case, it is calcium chloride, which is ionic, which means water is going to be our solvent. And that means our normal freezing point is 0 degrees. And if we go to that table, our freezing point constant is our 1.86 for water. So again, that is how we would get those based on water being the solvent. In this case, we are given the molality. We have the Kf. We could also find our change in freezing point temperature. Remember that what they gave us here, which is the temperature of the solution where it freezes at minus 0.27 degrees Celsius. So once again, the change in freezing point temperature is the temperature of the solvent minus the temperature of the solution. So that would give us our solvent is 0 degrees Celsius minus 0.27 degrees Celsius. This once again is how the negative goes away, and that will give us our change in freezing point temperature. Now that we have our change in freezing point temperature, we could solve for I here, and I would equal our change in freezing point temperature divided by our Kf and our molality. So that would be 0.27 degrees Celsius divided by our Kf of 1.86 degrees Celsius times molality. And we didn't need to calculate it this time. They actually gave us the molality of the solution, and that is 0.05. The m's will cancel, the degrees Celsius will cancel, leaves us just a number, which is good. So 0.27 divided by 1.86 divided by 0.05. gets us a 2.9. We would expect the I value for calcium chloride to be 3, as we just talked about, right? As you get 1 calcium and 2 chlorides. So this is pretty darn close. Any questions on that there? So again, if it's ionic, you do need to incorporate that I into your calculation. Simply just do it based off the formula. Will give you basically what I would equal. However many ions basically it breaks apart into will give you that number. Any questions on that there? All right. I think that's a good place to stop, I think, at this point. All right, let's lay it up there.